All right, we're going to be looking at section 2.3, Introduction to Techniques of Differentiation. All right, so in the last section we learned the derivative, like f prime of x is equal to the limit as h approaches 0 with f at x plus h minus f of x all over h. Well, in this section we're going to learn an easier way for taking a derivative of a bunch of functions without having to go through this limit thing every single time, okay? So let's see. First of all, let's suppose that c is a constant. The derivative of a constant is equal to 0. And then we have the power rule. If r is any real number, then the derivative with respect to x of x to the r is going to be r multiplied by the front times x to the r minus 1. All right. So now that we have the power rule and we know the derivative of a constant, we won't have to go through the limit definition every time for this stuff. Suppose we're told to find, and in part A we're going to have the derivative with respect to x of 7, say. So we're taking a derivative with respect to x of a constant. We just said that that is 0. No work to be done there. Part B. Suppose we have the derivative with respect to x of x cubed. Well, the important thing is you have the derivative with respect to x of x, okay? And it's x to an exponent. So what do we do in this case? We take that 3 and multiply it by the front, and then we say what we're left with is x to the 3 minus 1, or x squared. Much quicker way to take the derivative than that limit. How about C? What about the derivative with respect to x of 1 over x to the 4th? Well, to do this, I'm going to do a rewrite, because think about the rule we just had, the power rule. It said, okay, the derivative with respect to x of x to the r. It wasn't 1 over x to the r, was it? So I'm going to rewrite this to look more like that form. In other words, I want just x to some exponent. So I'm going to say this is the derivative with respect to x of x to the negative 4. Remember, you can bring this term up to the top, or this x up to the top, as long as you put a negative in front of that exponent. Now this is like that form, so I'm going to take the derivative like I did in the last example. We're going to say negative 4 times the front and reduce this by 1. What's negative 4 minus 1? Negative 5. Well, I could do a rewrite. I could call this negative 4 times 1 over x to the positive 5, which is the same thing as negative 4 over x to the positive 5. Remember, if you forget things like these exponents, dealing with negative exponents or whatever, go back and review some things. Like go to Khan Academy or a website like that, and look for practice on how to deal with negative exponents of variables. All right, D. D, what do we have? The derivative with respect to x of x to the 1/2. It doesn't matter that we have a 1/2 there. We still treat it the same way. We say, okay, 1/2 times the front, so 1/2 times x, and reduce this by 1/2. What's 1/2 minus 1? That would be negative 1/2. But let me clean this up. Let me write that with a positive exponent. So I'm going to say 1/2 times 1 over x to the positive 1/2. Or I could say 1 over 2x to the 1/2 would be one way to write my answer. Another way is you could say 1 over 2, and x to the 1/2 is the same thing as the square root of x. So either one of those will work. E. How about the derivative with respect to x pi to the 1/2. Pi to the 1/2. Now, don't let this fool you. Our power rule said what? The derivative with respect to x of x to the r. Notice how you had the variable x with the variable x. What is pi to the 1/2? That's just a number, right? That's a constant. That's about 3.14 to the 1/2. So what's the derivative of a constant? Derivative of a constant is 0. Let's see. How about E? That was E. How about F? F, we're going to have the derivative with respect to y of y to the 3/2. Now, this power rule still works because it doesn't matter if it's x here or if it's y here or z here, whatever, as long as this matches the variable on the inside. Notice the y down here, the derivative with respect to y matches the y there. So I'm going to use that power rule. I'm going to say 3/2 times y, and then subtract 1 from that. What's 3/2 minus 1? 1/2? That could be an answer. Another one could be 3/2 square root of y. Either one of those is fine. I'll tell you what, let's throw another one in here, G. Just to get y'all a little more used to this, G. Part G. What if I have the derivative with respect to theta this time of, I don't know, maybe something like the cube root of theta. Now notice my theta matches theta here, so that's good. But remember how I want this written? It doesn't matter if it's x or theta here. I want it written as to an exponent. So I'm going to do a rewrite. I'm going to say the derivative with respect to theta instead of the cube root of theta, what's another way to write that as an exponent? Theta to the, remember there's an understood 1 right there over that index of 3. Well, let's apply that power rule. We're going to have 1/3 times theta, and then subtract 1 from this. If I subtract 1 from that, I get negative 2/3. So that gives me 1/3 times 1 over theta to the positive 2/3. And if I multiply straight across, I get 1 over 3 times theta to the 2/3 is one way I could write my answer. How else could you write your answer? 1 over 3 times the cube root of theta squared is another way. All right, now that we looked at the power rule, we looked at the constant rule basically, we can look at a constant multiple rule. Constant multiple rule that's next in your notes. What does this read? This reads, if f is differentiable at x and c is any real number, then c is also differentiable at x, and we have the following. The derivative with respect to x, c times f of x, where c is a constant, okay? That's going to be equal to taking the c and pulling it to the outside and taking the derivative of f of x. Well, let's do an example. How about the derivative with respect to x of 8x to the 5th? Now notice this is of this form. C happens to be 8 here. So what I could do is I could rewrite it, pull the 8 to the front times the derivative with respect to x of x to the 5th, and that'll give me 8 times 5x to the 4th, or we could say 40x to the 4th. Now, what most people do here is they just do it this way. They just say, okay, the derivative with respect to x of 8x to the fifth is, they think, okay, well, I think if I pull the constant out here, I'm going to have to multiply it anyway. So I'm going to say 5 times 8 is 40, x to the fourth. Either way. Let's look at sum and difference rules next. Sum and difference rules. Your book says if f and g are differentiable with x, then so are f plus g and f minus g. So it writes it this way: the derivative with respect to x of f of x plus g of x is equal to the derivative with respect to x of f of x plus the derivative with respect to x of g of x. So what does that mean? That means if I'm taking the derivative of two functions being added, I could take the derivative of the first function, then add it to the derivative of the second function. Same thing works with subtraction. If I have this f of x minus g of x I'm taking a derivative of, I could take the derivative of f and then subtract the derivative with respect to x of g. All right, now very careful, very, very careful here. We do not have a rule that says this. That right there, we're going to say a big no. Definitely cannot do that. I see that all the time on exams. We cannot do that. We're going to see later how we handle that, okay? Probably be in the next section. But for now, you cannot simply just say, okay, if I have two things I'm multiplying together, two functions, and I'm taking a derivative of them, I can take the derivative of each one. No, it does not work in general. But these do work this way, okay? All right, so let's see. Let's talk about the derivative, okay? What was their definition of the derivative? What was their definition of f prime of x? We said in the last section, the derivative is written as f prime of x one way, is the limit as h approaches 0 of f at x plus h minus f of x all over h, right? We said that was the definition of our derivative. Which I could say, okay, another notation for this is d over dx. I could say of f, the derivative with respect to x of f is equal to the limit as h approaches 0 of f at x plus h minus f of x all over h. In other words, I just replace this notation with this one. So let me ask you this. What would this be equal to? The limit as h approaches 0 of g of x plus h minus g of x all over h. I'm going to say that's equal to. This is really the same thing as that, but we have our function g, right? So I could say it's equal to this thing, but with g right there. So I could say this is equal to d over dx of g of x. Let me make sure that appears in the view of the camera here. And guess what? It does not. So let me rewrite this stuff over maybe here, okay? So what we're saying is, we're saying the limit as h approaches 0 of f at x plus h minus f of x all over h is equal to the derivative with respect to x of f of x. Let me make sure that one appears in the view screen. This will be so nice whenever my tripod comes in from Amazon that I ordered for this. You should see the funky setup I have going on right here for my camera. All right, then we said this. The limit as h approaches 0 of g of x plus h minus g of x over h is equal to the derivative with respect to x of g of x. Keep this in mind, okay? Keep that in mind. By definition, this is the derivative of f. This is the derivative of g. All right, let's look at something in math called a proof, okay? In real life, we use the word proof wrong a lot. You'll watch a court show, they'll say, that is proof that you committed a crime. Well, not really. What they usually mean is say it's evidence, okay? Proof means there cannot be another way, okay? A lot of time whenever we're doing stuff in math, we just say, okay, well, it worked once, it worked twice, it worked 3 times, it worked 4 times, it worked 10 times, so it works every time. Well, that's not a proof there. It just works for those 10 times you try. For a proof, you have to show that it works every single case, okay? For example, what if I was a little kid, just learning language, just learning what things were and so forth, and I've been exposed to 3 dogs, but all 3 of them had only 3 legs. I would think all dogs have 3 legs, right? So I would say 1 dog had 3 legs, 2 dogs had 3 legs, 3 dogs had 3 legs, therefore all dogs had 3 legs. Well, I would be wrong because I didn't consider every case. All right, let's consider every case here. Let's prove this. Let's suppose we're going to prove this part right here, okay? So what I do is I start out with this part, okay? The derivative with respect to x of f of x plus g of x. Now notice I'm not showing it for particular cases, like what about whenever f of x is 2x plus 3? Or what about when g of x is x cubed? No, I'm showing it for any f of x, any g of x, okay? All right, what can I say about this? Well, according to my definitions here of derivative, the derivative is the limit as h approaches 0 of my function evaluated at x plus h. My function this time is all this. So f at x plus h plus g at x plus h. So I'm evaluating the stuff at x plus h minus this stuff evaluated at x. So minus f at x plus g of x all over h. By definition, that's a derivative. That's the derivative of this by definition. Well, let's see. That's equal to the limit as h approaches 0 of f at x plus h plus g at x plus h. And if I distribute a negative here, I get minus f of x minus g of x all over h. Well, let me rearrange some stuff here, okay? Let me put maybe this minus f of x over here and swap it around with this g at x plus h. So I can say that's the limit as h approaches 0 of f at x plus h minus f of x plus g at x plus h minus g of x all over h. Well, I could break this up. I could say this is the limit as h approaches 0 of f at x plus h minus f of x all over h plus g at x plus h minus g of x all over h. Do you agree? If I add this back up, I'll get the step above. So they're equivalent. All right. What about our limit? Didn't we talk about our limit laws in the first chapter? We said that if I have the limit of two things being added, I could take the limit of the first one and I could take the limit of the second one. I'm going to have to come over here because the other stuff's in the way. But I'm going to have the limit as h approaches 0 of the first thing I have, x plus h minus f of x over h, plus the limit as h approaches 0 of the second piece I have is, or the second sum I have is g of x plus h minus g of x over h. This part right here looks familiar. To me, it looks like that part right there, right? So what can we say that's equal to? D over dx of f of x. D over dx of f of x. That's what all this part is. Plus, what does this part look like? That part looks like this, which we said was d over dx of g of x. D over dx of g of x. I started with this right here, right? Did this limit definition, and what did I get to? I got to this right here, which was what? The same as that, right? So I just proved that this part is equal to that part for all f of x and g of x. How you like them apples? All right. Let's use this now, okay? We proved this. I just wanted to show you a proof because those of y'all going on the Calc 2, y'all going to see more proofs. Kind of prepping y'all for that. All right, let's see. Suppose I have an example and we have part A. What about the derivative with respect to x of 5x squared minus 3 over 2x to the fifth plus 5 times the square root of x. Now, I just proved the sum one. I'm not going to prove the difference one just because, you know, it takes so much time. But it extends to 2 functions, 3 functions, 4 functions, 5 functions, or whatever. In other words, if you're taking a derivative of things, of parts being added and subtracted, you can take the derivative of each one of them, okay? Now I'm going to do that. I'm going to take the derivative of each one here. Now this one won't be hard to take the derivative of, but this one is because of how it's written, and so is that one. So I'm going to do a rewrite. I'm not going to take a derivative yet. I'm just going to bring down the symbol. I'm going to say, okay, 5x squared is fine how it is. However, this one, it'll be easier if I move this up to the top. So I'm going to have negative 3 over 2. Now the exponent's just on the x. So I'm going to move the x up to the top and call that x to the negative 5 plus 5. Now this one's hard to take the derivative of because it's written as a square root instead of x to some exponent. So what's understood right here is my exponent of 1. What's understood is my index, 2. Remember, it's x to the, whatever this number is, over that number, 1 over 2. All right, I'm going to do one more rewrite here before I take a derivative. Okay, so this is 5x squared minus 3 halves, but yet I could factor this out to the side and call that x to the negative 5 plus 5x to the 1/2, and that'll make it even easier for me to take a derivative of. Now let's take the derivative of each difference and each sum here. What's the derivative of this? 2 times 5 is 10, x to the first, minus 3 halves times, what's the derivative of this part? Negative 5 times x to the what? Remember, subtract 1 from that. Negative 6. Plus 5 times, let's take the derivative of this part. That's 1/2 x to the negative 1/2. All right, so this gives me 10x, that's 5. But let's multiply this stuff. Negative times a negative will give me a positive. And 5 times 3 gives me 15, and that's over 2. Times x to the negative 6. Plus, this is 5 halves, x to the negative 1/2. Now, I want to clean these up, not have negative exponents on them. So think about what they are. They're really over 1, each one of these, right? So I have 10x plus, and if I multiply straight across, I get 15x to the negative 6 over 2. Plus, if I multiply straight across, actually, let me write that a little better. That was 5 halves times that. If I multiply straight across, I get 5x to the negative 1/2 over 2. Well, that's 10x plus, now I could take this x to the negative 6 and bring it to the bottom with that 2, and that becomes x to the positive 6. And I'll have 5 over 2, and if I bring this x to the bottom, it gets x to the 1/2. There we go. Or you could write that as the square root of x. That's fine. Part B. Let's suppose for part B, I have the derivative with respect to y, y squared minus 5y cubed all over y. Now I'm told to take the derivative with respect to y at this. All right, think about your rules you had. You had the power rule, you had the what else? You had whenever you have a sum and a difference a rule, but you didn't have a rule for multiplying. You didn't have a rule for dividing either. So there's no rule that we've seen yet for this. So what you do in this case, in general, before you take a derivative, is you try to simplify what you're taking a derivative of. So if I try to simplify here, I could do a rewrite. I could say that's y squared over y minus 5y cubed over y. So y squared over y minus 5y cubed over y. Well, let's bring down our derivative notation. Y squared over y is y to the first. Minus, this will be 5y squared if I divide these out. So what's the derivative of y with respect to y? It's 1. How about the derivative of this part? 2 times negative 5 is negative 10. Y to the first. Wait. How'd you get 1 out of that? Well, let me show you. What's my understood exponent right here? It's a 1, right? So what do I do according to that rule? I take 1, multiply it by the front, and then I reduce this exponent by 1. 1 minus 1 is what? 0. Well, that's 1 times, what's any number to the 0? 1. Minus 10 times y. What's 1 times 1? 1 minus 10y is my derivative. So we talked about taking derivatives. We talked about we're taking a derivative of 2 things added. We can take the derivative of each one and add it. We talked about we had a derivative of 2 things being subtracted. We can take the derivative of each one of them and subtract. What about some other derivatives, what we call higher derivatives? If I have f prime, that's my first derivative. I'm just going to abbreviate here. First derivative. Another way to write that is d over dx, okay? That's what we've been looking at so far, the first derivative. What if I want to take a second derivative? The way we denote that here is f double prime is my second derivative, and that's d. It almost looks like an exponent of 2 right here. and an exponent of 2 right there. A lot of people say, when they're first reading this, d squared over dx squared. No, it's really second derivative of x. Or, I'm sorry, second derivative with respect to x. Second derivative with respect to x. For a third derivative, over here I denote that y triple prime. That's going to be my third derivative. And the way I write that is like this. The third derivative with respect to x. Now, whenever we get to the fourth derivative and so forth, we start putting like a number up here because it gets too cumbersome to count the little tick marks and so forth. So fourth derivative, and over here we denote it the same way basically. You just put a 4 and you keep going like this, okay? So that's just notation there. Let's put it into practice. Your example says if f of x is equal to 5x cubed plus 2x squared plus 13x plus 450, comma, find this. So that notation says find a fourth derivative of f. So to find a fourth derivative, I got to start out with the first derivative, the second derivative, the third derivative, then I can find a fourth derivative. So let's find our first derivative, f prime of x. 3 times 5 is 15, x squared. How about this one? 4x plus 13 plus, well, that's just 0 if I take the derivative of it, right? Because it's a constant. So really, I don't have to write the plus 0. Let's look at my second derivative, f double prime of x. So take the derivative of your first derivative, and that gives you second derivative. So we get 30x plus 4. Remember, that's just 0, right? To get your third derivative, take your derivative of your second derivative. So that's 30 plus 0, or just 30. So my fourth derivative will be the derivative of this third derivative. What's the derivative of a constant? 0. And actually, anytime you have a polynomial, if you take the derivative enough times, you're going to get to 0. Enough times here was 4. All right. What about